Just get started right here. How many of you have any of these things at your company? Release engineers, QA departments, things like that. Chef, Puppet. Okay, cool. So Netflix doesn't have any of those things. But what we do have is thousands of releases a day. Actually, this says hundreds, but it's probably closer to thousands at this point. So my name is Jeremy. I work for Netflix, and I'm here today to tell you about our DevOps culture and I guess what's now referred to as microservices architecture, although we've been doing it for about 7 years, and we call it something else. So we'll get into that in a little bit. How many of you are familiar with Netflix? Excellent, good. Thank you for paying my salary. Just in case you aren't, we're a streaming service on the internet, serve a bunch of people in a bunch of countries. But more importantly, I'm here today to tell you about the Netflix way, basically how we operate our service, how we do what we do, and how we do our development and our deployment and things like that. I'm going to tell you about how we build stuff for free, and we have fully automated tools and practices and things like that, fully automated machine images, and importantly that we have dev and ops run by the same folks. So this is an important point here that I'll get into later, and also one that was brought up during the keynote in the whole microservices architecture thing. And then I'll tell you a little bit about our redundancy as well. I'll also tell you about our culture of freedom and responsibility, how we hire people who we consider adults. They can do whatever they want, wherever they want, whenever they want. They'll have they have access to all the code everywhere, all the time. Anybody can change anything. And generally speaking, this actually works. Things usually don't break because of this freedom. And that's because while developers do deploy when they want to, they also get called at 4 in the morning. So, like Neil said during his keynote, if if you're the person getting called at 4 in the morning, you're much more likely to write higher quality code, or if your buddy is the one getting called. So this works out really well. It also means that each team gets to manage their own capacity and their own cadence for development. So different teams have different cadences. Each one sort of agrees on what they want to do. So this freedom and responsibility is really important. The important point here is that developers own their product from beginning to end. So if the customer isn't happy, the people who pay us money, then the developer shouldn't be happy, because that means that they need to do something differently. And so what's really great here is that it makes every engineer at the company basically individually responsible for the happiness of our customers. And that's good, because that means that we have lots of happy customers that way, because our engineers want the company to do well. And so this is a really important point, that it's the way we design our entire architecture around people and code are designed to make our customers happy. It's designed to make sure that our engineers are focused on that. So a lot of this we do through automation. We believe in automating as much as possible. We automate application configuration, startup, deployment, everything. We do some of this using standard base image. So we don't update machines that are running, we just replace them. We have sets of tools that manage all of these systems, and we have automated code deployment. So one thing that's important here that we'll get into later is, while we have a service-oriented architecture or microservices, we do have some centralized teams, because what we found was that having completely decentralized systems didn't work out so well, because then you get a lot of duplication of effort. You get a lot of people doing the same thing but poorly, because they're not experts in it, nor do they want to be or spend the time. So we have some centralized teams, particularly the teams that provide the tools for deployment and for testing, and also the base platform. So I'll get into that more later. We do what we call, building for, or what I call building for 3, where basically we have 3 of everything running. Our data has at least 3 copies in production. Generally speaking, services in production are going to be running at least on 3 different instances, and we do this for reliability. And so I'll get into that a little bit later as well. But first, I want to take you on a brief journey through history. So, back in the day, we used to have a bunch of users and a few computers, and maybe like a mainframe or something, right? One big computer. And the important part here is that that big computer in the middle, it never failed. it was very expensive, very big, had a lot of redundant parts, and it was designed to just never fail. And if it did, your company was really screwed. And so we built our architectures around this assumption that that one big main system is never going to fail. But that's not what we have today. What we have today is we have that same number of users, but we have a ton of different computers all over the place, different systems, and we don't have that one big one. And we have people with their mobile devices and with their their own laptops and all that. And so what we've essentially done is we've made this movement here from the mainframe to the client server to the commodity, all the way up to, what happened there? All right, all the way up to the web scale. And so this is how we've sort of designed our systems, right, around this idea that we used to live in a world where the assumption was that nothing breaks. But that's just not true anymore. So scale breaks hardware, right? The bigger your scale, the more often your hardware is going to break because you need more of it. And speed breaks software, right? The faster you're doing your development, the more often your software is going to break. And so, as one of my former coworkers used to like to say, speed at scale breaks everything, right? So we had that 80s mainframe cycle where it cost you a lot of money to do development. You had to basically bet the entire company on a new feature. Then we went on to the 90s where it wasn't quite as expensive anymore, but it would still take a lot of time to execute. And there was usually an entire division of people who, if that product failed, had to get let go because we don't have any money anymore, right? And then we started to get into this whole agile idea where it wasn't that expensive. The cycles were a few weeks, and it's pretty good. You could, you might have to throw away a product feature if it didn't work out, but that was about the cost of failure. And we had this waterfall model where, the product manager would just conceive of the idea, and then the developer would write it and pass it over to QA, and then QA would pass it on to ops, and at the ops guy would curse everybody because it would never work right the first time or the third time, and then finally the BI analytics person would tell you if it actually worked. And as we've moved forward, this whole idea of the cost and the size of risk decreasing and the rate of change increasing. So we came across, upon what we call cloud native, and what most everyone else calls microservices. So this is where we have tens of thousands of instances. They're churning over daily. We churn over our instances about 70% in 2 weeks and about 90% in a month. And thousands of nodes of storage with petabytes of storage. And when we first started telling people about what we were going to do, about how we were going to run everything in the cloud, and it was just going to be one small service for every little thing, they said that that's not possible, right? Nobody can do it. It's not going to work. You must be lying. There must be other stuff you're doing that isn't there. But as we kept doing this, they started to believe us. And so then they started saying, okay, but nobody else can do it. You're the only guys who can do this. You're the only people who can run this architecture of lots of small services in the cloud that are always turning over. But we've been doing this for about 7 years now, so people have started to believe us, and that's good. They even came up with the term for it, microservices. And we think this is still the right way to go. So this is why we like to tell everybody about what we're doing, because we really think everybody, not everybody should be doing this, but we want everybody to at least think about doing this because it's probably going to be good for them. So as I said, we run a service-oriented architecture. It's a lot like NASA, how they have the one person there who's responsible, but it's backed up by a whole bunch of servers. And we like to say at our company that we are highly aligned and loosely coupled. So what does that mean? What that means basically is that each dev team builds a service, and although we don't phrase it like Amazon does as the two-piece team, we have mostly small teams working on services. Oftentimes, one small team is working on a bunch of different services. The way that they communicate with each other is via API. So that's the contract. The contract is the API between the services. Sometimes it's the library. So you as the service owner will produce a library that everyone else can use, and then that's your contract instead. But that's still an API. It's just, in that case, a Java API instead of an HTTP API. But either way, it's the API that's the contract. And what this does is it gives everyone a lot of chance to go quickly because they can make changes to their service, and as long as they maintain their API, everything will be working out great. It's much the same way that you are probably producing your service for the consumer internet. It's still going to be an API. So some of the advantages to doing it this way are easier scaling. So each team is responsible for its own scaling and for its own capacity planning, which is really nice because you'd only have to worry about a small little problem. You don't have to worry about the entire ecosystem. Although we do have a centralized team for worrying about that. You can identify problematic code paths much easier because it's only a small chunk of code that's changing. And each team is deploying their own code, and it's going to change in their own small time scale. And so that narrows the effects of change as well, right? And you get this nice benefit of more efficient local caching because each service is only responsible for a small little thing. And one of the other nice things about this architecture is that this is the anatomy of an outage, right? Is the worst kind of outage you can have is the kind where PR has to get involved, where your customers notice it and they have to put out statements and things like that. And then it moves down the stack from there. And by doing this service-oriented architecture, what it lets us do is get to the point where hopefully we're down here in the green zone, right? Where it's, maybe features are getting disabled because one service is not behaving correctly, or it's to the point where there's no impact noticed at all because one server fails and it just goes to the next. And that's really our goal state. Our goal state is to have all of our outages be to the point where our customers do not notice, because that's what we want. We don't want our customers to know that we are having issues. So a real basic diagram of how Netflix works. We have thousands of different types of clients that we support, and they all talk to the API basically. And then that API fans back out and talks to all the different services to get the data that it needs. And the API actually has its own little runtime engine in it so that UI developers can do things like create a chunk of code that reaches out to, say, the 20 different APIs that they need info for and coalesce that into a single response that goes back to the client so that the client only has to make a single request to the API to get what it needs. And so basically each client UI team is creating their own custom API endpoint that provides exactly what information that UI needs. And this is helpful for reducing the number of requests that a client has to make over the internet, which is very flaky. And it also means that it's much more cacheable for each individual UI. So we talk about the browse, play, watch. Basically, there's 3 different parts to the Netflix experience, each one driven by a different set of APIs, although that's being merged together. And what's important to note here is that that last one on the bottom there, the watch part, is run out of our CDN. And our CDN is our own hardware infrastructure that we have set up all around the world in the areas that we serve. But we still manage those systems the same way that we manage our code in Amazon. We still deploy fully baked machine images out to those physical servers. So what we're doing here really does apply to everything. And a lot of our system choices assume that things are going to fail. So that's really the crux of it all, right? Is that we assume failure. We assume that nothing is ever going to work as we intend, and we account for that. We write all of our code in a defensive way, assuming that things are going to break. And we worry about how reliability is really just a balance between money and reliability, right? If you have infinite money, which our company does not, and I assume yours doesn't either, then you can have really good reliability, potentially perfect reliability, but that's not the real world. The real world is that it's always going to be a balancing act. And the last really important philosophy thing is that we follow the monkey theory. How many of you have ever heard of the chaos monkey? How many of you have heard of anything other than the chaos monkey, the other monkeys? Excellent. So we have a whole lot of monkeys. I'm going to show you those in a little bit. But basically the idea here is that we simulate things that can go wrong. So we actually break things in production on purpose to see what's going to happen. And we also look for things that are different. By running a whole bunch of the same service, and 3 at least, we can look for outliers. We can look for things that are different and just get rid of them. So like I said, pretty much everything I'm talking about today is how we run in the cloud, but almost all of these things will apply just as well to someone running in a data center or a private cloud or anything like that. So now let me tell you a little bit about how we actually do what we do. So like I said, we've built ourselves a global platform as a service. It's a service-oriented architecture, and it has REST endpoints. So some of the important features of that is that it supports a lot of the stuff that everybody needs. So this is our platform. It includes support for multiple regions, multiple accounts, cross-region, replication, all of that sort of stuff that everybody writing a service in Netflix needs. And we built it on top of Amazon Web Services. So AWS provides us stuff that not only Netflix needs, but basically stuff that everybody needs, right? So they provide machines and IP addresses and load balancers. And so the idea here is that we rely on Amazon because they do what we call the undifferentiated heavy lifting. They do the stuff that every company is going to need to run a service. And then we build a platform on top of that that everyone at Netflix is going to need. And then our developers only have to worry about writing the code that their service is going to support. It starts with a base image, and I'll get into more details about that one in a little bit. This is our basic architecture. And then there's also a bunch of data. And so we do a whole bunch of stuff with the data. And so I'm actually going to start by talking about the data, because that's at the bottom of the stack. We do have different data stores for basically every service. We have a team that runs all of our data storage, but they provide individual services for each service team. Now there is a few general data stores the teams can use, and that's usually where everybody starts. They start with an individualized data or with the shared data store until they are using it too much, causing an excessive load, and then the data team will basically come and say, hey, we're going to move you off to your own storage. It's going to be totally seamless to you. We'll let you know when you're done. And then they maintain the Cassandra infrastructure, which is where we store pretty much all of our data. Their caching infrastructure, and also we do use some MySQL. One of the key tenets of our data is that shared state should always be on a shared service. There should never be a chunk of information that only lives on one machine or one instance, and it really shouldn't ever live in the service. It should live on a shared data service. We start with what we call EVCache, which is a library that's built on top of Memcache. And this is open source. You can download this from our GitHub page. It does some things that Memcache does not, like automatically replicate between regions and worry about affinity, cache affinity, so that when your service is going to get something from the cache, it's getting it from the most local cache and not reaching across zones or data centers. And then we also have Cassandra. And Cassandra is sort of the big data store for us. Almost all of our data is stored in Cassandra. Why did we choose Cassandra? We chose Cassandra because of its availability over consistency. We're more concerned about somebody being able to play a movie than having our data be 100% accurate. Because at the end of the day, our customers don't give a crap if we stored all of the data perfectly. What they care about is watching a movie. Also, it does writes over reads. So we like to joke that we're a logging service that happens to play movies, but it's sort of true. We actually take in a lot of data from the client, and this is how we provide our customer experience, because we have a lot of data about their viewing habits and what they like, and so we can give them what they want. And also because we know Java and it's open source, and that was a big one, right? It's open source, but it comes with support because you can pay for support, aka the Red Hat model. And we really like that. And we like the fact that we can dive into the source, that we can contribute to the source. We have contributed to the source. A lot of the multi-region stuff in Cassandra was written by Netflix. And it also provides us a lot of technical benefits, right? It has fast writes. It has fast negative lookups. It's got easy scalability, which is not entirely true. Generally, Cassandra you have to scale in powers of 2. However, that's getting fixed with the latest version with virtual nodes. And it's distributed, right? We can take out any one Cassandra node, and we don't have to worry about losing data or losing the ability to read and write from that data store. We store a whole bunch of really boring stuff in Cassandra. We also store some slightly more interesting stuff in Cassandra that you might actually care about, like video quality and network issues, usage history, pretty much everything. And our Cassandra architecture is designed in a way so that it's most reliable. So if you look at this chart, I've added some red lines to it, which represent the separate regions or separate zones in Amazon, the different data centers. And if you look closely, you'll notice that each chunk of data exists in each zone. And so this is how we lay out our data. We do it in such a way where there's 3 copies of each piece of data, and they're spread across the 3 different zones. The reason we do this is so that we can lose any one entire zone and still continue to run without issue. And we do this exercise about once a month, actually a little bit more often, where we take out an entire zone. We started with one set of Cassandra in the US East, then we expanded to Europe and added a second one. And that's when we wrote all of the global replication. So there's a bunch of replication that happens between, because every Netflix account is good all around the world. So we have to make sure that your account data exists everywhere. And then other pieces of data don't replicate. And then last year, we did a big project to make ourselves more resilient to failures in the United States, regional failures. And so we added a third region over in US West. So now we had to deal with replicating data across 3 different places. And all the data is replicated from east to west. So now we basically have at least 6 copies of everything in the US and 9 copies of basically all of your account data so that it's good everywhere. And this is how we maintain reliability with our data store. So now I'll tell you a little bit more about our tools and how we actually do our deployments and things like that. How many of you heard of Asgard? Okay, so Asgard is our cloud orchestration software. It's what we use to do all of our, well, I don't want to say all of our deployments, but it's what we use to do a lot of our deployments. So what we've essentially done is we've built a system where you as a developer, all you have to do is basically go in and modify your code. You check it into the repository. We use both Git and Perforce, although we're moving more towards using Git. That kicks off a build in Jenkins. So what it's building is actually a complete machine image. So we believe in this idea of building complete machine images for homogeneity, for one, and for 2, because we don't want to have to deal with making sure that any changes got pushed out properly to all the different machines. So when you're running a huge cluster of machines, it helps to know that those machines are all the same because they can't be any different. And what that machine image actually defines is a whole bunch of things around, not just code, but it defines things like which load balancer configurations, launch configurations, security configurations, and all of that. So that all of that is baked into the image. And so what we do is we produce this image from Jenkins, and it actually produces a fully runnable piece, machine. And then we start the deployment process. So what we do is we launch that, we have our old code running, and so we actually launch the new code right next to it. We don't do a rolling push or anything like that. We actually launch a whole brand new cluster right next to it, and then turn on the traffic to that new cluster. And we watch for a while, we see how that goes. Then we turn off traffic to the old cluster, wait for a peak period, which is usually overnight. And if we come back and everything is happy, then what we do is we actually delete the old cluster, and then the new cluster is just running. And so what this does is it makes our deployments very quick, because all you have to do is wait for the launching of the new cluster, and you can move the traffic over very quickly, and you've got your new code running. It also makes rolling back really quick and easy. So imagine this process again, but we bring up the new cluster, and maybe things aren't looking so good, but we're not really sure. So we actually push the traffic over to the new cluster, and we realize, oh crap, everything is broken. This is not good. But we don't have to wait to roll back. We don't have to wait for redeploying everything backwards, right? We just shift the traffic back, and now everything is happy again. And we have that old cluster sitting there. We can do whatever we want to it. We can trickle some traffic back to it for debugging. We can go into the logs, or we can just delete it. It depends on what that team wants to do, what kind of experimentation they were doing. Maybe they deployed something that they were pretty sure was going to break, and so they already know what it is, and they just delete it. Whatever it is, it gives the developer the flexibility to do whatever they think is the right thing to do. And that's really sort of the theme of all of our tools, is all of our tools are designed to be self-service, to give our developers the chance to do what they think is the right thing to do. Some examples here of Asgard of what that looks like. So here's an example where both clusters are taking traffic. And then here's an example of one cluster being disabled, the one on the left there. Some more examples of what Asgard does for us. Asgard, being our cloud orchestration software, lets you know what everyone else is doing as well. So you can see all the different clusters that are running. We actually have about 600 or so different services running at this point, 650, somewhere around there. And then we have lots of clusters running. So since people are doing deployments, their clusters are versioned, and so you can also see the list of clusters. And so there's usually like 1,000 clusters running because everyone's in the middle of a deployment at some point. So what we've done is essentially we've moved the granularity up from an individual instance to a cluster. And this is really important. This is actually what has really helped us move forward, is because we don't care about individual instances anymore. If one instance is misbehaving, we just delete it. If something else is wrong, we're looking for things that are different and we just get rid of them. Only if it keeps happening over and over do we actually dive in and think, oh, it might actually be our software that's the problem. But our initial assumption is always that it's hardware, and that's Amazon's problem. So we don't have to worry about it. We just delete it and let Amazon take care of it. And so that has really enabled our developers, because they no longer, even though they're running their own services, they don't have to have the expertise to dive into individual instances. So that means that the team doesn't have to have, every team does not have to have somebody who's an expert at doing that kind of thing. So why bake, right? The traditional method of installing software is first you launch your generic machine, then you have your Chef or your Puppet or whatever, and you install your libraries, and you install your packages and all that. Whereas in Netflix, like I said, we launch a single working machine, or we build a single working machine and we launch it. The process, this is the pipeline generally for doing that. So you check in your code, it runs through your ant targets, etc. Your testing can be in here. So each team determines its own testing methodology and whether they're even going to do testing. Some teams have very rigorous testing. Some teams do test-driven development. Some teams have unit tests, some teams have integration tests, some have both, some have neither. It's completely up to the team how they want to do it. Some teams have their 2-week cadence and they do all their testing, etc. Other teams will deploy new code 6-8 times a day with no testing at all. Their testing is running it in production and seeing if it works. Which isn't such a bad way of testing, honestly, as long as everybody has proper fallbacks and works around that. But at the end of the day, this pipeline produces an application bundle which goes up into our Yum repository to be installed on the base image. A quick sidetrack here. To create our base image, essentially what we do is we just take Amazon's Foundation Linux or Ubuntu's now, so we're doing Ubuntu as well. We launch that into our bakery, and then we install all the basics that everyone's going to need. We install Java, we install Python, we install Apache, Tomcat, whatever it is that pretty much everyone is using. And then what we do is we build that base image. So that's the base machine image, and then that's just sitting in our bakery. And our bakery is also open source. It's called Ominator. It's also on our GitHub page. And so now we get to that final step of how do we actually make that application image. So we take our application bundle that we just created with Jenkins, and we install that onto our custom base image using the bakery. How does the bakery work? The bakery basically just loads up a disk image with the base image, installs the package on it, and then creates a new Amazon machine image from that. Uploads that machine image into Amazon's data store in S3, and then it's ready to go. And then it goes back to that process you saw before with Asgard, where once it's ready to go, that process takes, it depends on what it is, but it takes somewhere between 7 and 20 minutes, depending on the load of Amazon and the bakery and the complexity and things like that. And then it's ready for launching and testing. Then the developer can launch it, see how it goes. If it looks good, it'll basically be marked ready for production, and they can immediately move on to production. We're actually working on some methods now where we're trying to reduce that time for testing by having it actually, when you check in your code, it'll just push it right out to an already running instance. At the same time, it'll build an image. So you can start your testing, and if it looks good, then by the time you're done, you can actually launch your existing image and test to give one final check just to make sure that something didn't get messed up in the process, and then go straight to launching. So we're always trying to reduce the time our developers have to wait. Right now, our cycle time is about 10, 20 minutes, depending on how long it takes for the person to actually write their code. So a little bit more about our base machine image. Our base machine image is basically composed of 3 different parts. It has the base OS itself, which has along with some stuff like Apache and things to serve, and then it has the compute language that you're going to use, and then the actual stuff the developer writes. And the ideal here is that as a developer, the only thing you have to do is write that application code. That's the minimum work that you have to put in as a developer in Netflix. You write your code, you check it in, it runs as a web service in the cloud. But what we do is we give our developers a lot of flexibility. They can change whatever they want in this system. They can do JBoss if they want to. I don't know why they'd want to, but they can. They can do rip out the entire compute language, right? So my group, we actually write mostly in Python. So we've ripped out the entire programming language part and replaced it. What we do is our developers can change any part of the system that they want to. It's all extensible, configurable. It goes back to this whole idea of self-service and letting people do what they think is the right thing to do. And then we do continuous integration, right? So each check-in results in a new machine image. We have a system called Mimir that we're working on, which is essentially a tool that describes a deployment. So what you do is you say, okay, when I check in my code, I want you to launch a machine and test. I want you to run these tests. Then I want you to launch a canary in production, and I want you to run these tests. I want you to compare the results. If they look good, I want you to run, do a complete new cluster. This is essentially what you describe. And so then what you do is once you check in your code, you just wait for all of those steps to take place. You get feedback throughout telling you, okay, your tests are running, your tests have passed, your canary is running, here's the results so far, your canary passed, we've moved on and we've launched into production, are you ready to destroy your old cluster? Things like that. And so what this does is this reduces our lead time, right? Our cycle time. And we're always looking for ways to improve this, to make this faster and easier for the developer. We really want to just get to the point where all you have to do is think of an idea, write the code in, and it's running in production. So that's what we're getting towards. So like I said earlier, we have some centralized teams. We have the team that provides all of these tools, these deployment tools, because what we realized is when we started in the cloud, everybody was doing their own thing. People decided they were going to use Amazon, and they started launching their systems, and everybody would configure their own system, and everybody would deploy it their own way. Some people would just do it by hand. Some people had some crappy scripts to do it, but there was a lot of duplication of work happening. So we've centralized that function pretty early on, this whole idea of deployment and testing and all that. And the other thing we realized is that a lot of people were writing the same code over and over again. How do I find the other services? How do I talk to the other services? How do I find Amazon resources? Stuff like that. And so that's where we came up with the Netflix platform. And that's our other big centralized team, is the team that writes the platform that everybody runs on. And this team represents about 1/5 to 1/4 of our engineering staff, the team that writes the platform itself. These are the logos for all of the parts of our platform that are open source. Our goal is to have our entire platform be open source as soon as we can, so that everybody else can use the same platform that we are. But what I'm going to tell you about now is some of the specifics of that platform. So on the left is what we call it internally. On the right is the external name. So the first I'm going to talk about is Eureka, which is our discovery service. It's basically application mapping. If I need to talk to the service that gets movie ratings, what machines are actually running that service right now? So because you need to know that, right? Because there's no easy way to find them otherwise, especially with all of the resources changing all the time. We have instances launching and instances disappearing. And so we need an always up-to-date directory of what machines provide what services. And so that's what that does. It keeps track of them, it does heartbeating, it makes sure that they're alive, etc. We have another one called entry points, or ETA. This is essentially a cache of Amazon's API. So it's very important for us to know the existing state of our infrastructure of our machines at all times. So, mostly for our monitoring systems, but for other systems as well. And so we've developed a cache of Amazon's API so that it's fast enough for us. The next one I want to tell you about is Ribbon. And we call it NIWS. It's the Netflix internal software load balancer, basically. So this is the software that actually, when you say, I need to talk to the movie rating system, you send the request to that, and that service is smart enough to say, okay, there's a copy of that running in your zone. I'm going to go to there. Oh, that timed out, so I'm going to go to there and keep track of, that one might be down for a little while. And so it does things like that. It keeps track of, it does intelligent routing, basically. It's also the layer that allows us to do some failure injection. So what we can do is we can put things into there like, say, we want to test what happens when the movie rating service is slow. So every time you do a request for that service, we want you to just do a sleep for half a second before you return the answer. Or we want you to randomly sleep for up to a few seconds. Things like that. So let's just, that by having all of the requests filter through this part of the library, it allows us to do failure injection. And that's another important part of this platform, is that it allows, by everybody using the same platform, it lets us do failure testing in a similar way across instances. We also have a couple of other things. So we have a property configuration. This is how we basically do feature flags. So, how many are familiar with concept of feature flags? Okay, cool. So this idea that you have a feature, you can turn it on and off. It's in your code, and you can turn it on and off for testing. Then this is also for just configuration variables and things like that. We call it fast properties, although really we should call it medium properties, because they're designed to not propagate instantaneously. Because the last thing you want to do is flip one property and have the entire system just stop working all at once. We have another one, the base system, called carry-on, which, if you're familiar with biology, basically means the fundamentals. This is essentially just sort of the base configuration idea of knowing about production versus test, and the real basics of what we have. But it means that everybody doesn't have to rewrite that real basic stuff of, if you want to write a piece of code that does something different in test than prod, you don't want to have to figure out if you're in test on your own. You just ask this base service. And then there's the logging. Logging is a big piece of it. We call it splits for J. Essentially, it keeps track of what happened. And then the last bit of library is the libraries that we use for storage. So we have preem and Astyanax. Preem is for configuring Cassandra. So this is our tools that we use that actually do the part about launching new Cassandra instances and putting the data in the right place and things like that. Also then Astyanax basically provides an OO interface to Cassandra to make it easier to use Cassandra and to take care of basic Cassandra stuff like connection pooling and host discovery and all those things with Cassandra that we don't want our developers to have to re-implement, because we really don't want them to have to go and find their data every time. Another one, EV Cache, which I mentioned before. This library that's a wrapper for Memcache. And then one thing that we used to have that we don't actually have anymore were these ideas of proxies. So this is how we moved ourselves out of the cloud, out of the data center and into the cloud. And I can tell you more about that later if you're interested. And so what this leads us to is on our open source page, we have what we call the recipe RSS. So it's a basic RSS reader. The timing works out really nicely. We launched this basically right around the same time that Google stopped providing Google Reader. It's not a replacement for Google Reader, though. It's not anywhere close to that good. Although it is open source, so you're welcome to run it and make it that good if you want. But what's important about it is that it uses all of those services that I just told you about. So essentially, this is our version of Hello World. This is our app that shows you as an open source consumer how our platform works, and it shows our developers how the platform works. So we put our developers through a boot camp when they first get to Netflix, and we make them all set this up and run it, and then modify it. And so this teaches them how to use our platform, and this is basically showing what our platform can do. On our GitHub page, there's a whole lot of other components as well that I didn't talk about, but I encourage you to go and look and see what we provide. Our goal here really is, we know that our advantage is not in how we run our cloud infrastructure. Our advantage is in our data. And so we're more than happy to share how we do our operations and our infrastructure, because the more people who are doing it this way, the more leverage we all have to to take advantage of that. And so that's really our philosophy behind open sourcing our platform, is we want everybody to be able to leverage the work that we've done so that they don't have to do it as well. Because then everybody can get to a point where their developers just have to write code. So now let me tell you more about the Simian Army. Like I mentioned, the Simian Army is not just, the idea is to simulate what goes wrong, find things that are different. The army is not just the Chaos Monkey. The Chaos Monkey is just the first of the army. We also have the Chaos Gorilla. So the Chaos Gorilla actually destroys entire zones, or data centers basically. And we run that drill about once a month, where we turn off an entire zone of infrastructure and see if everything keeps running. And the basic philosophy behind this is, you're not going to know if you're resilient to failure unless you actually practice, you cause failure. Right? Amazon calls this game day exercises, so do a lot of other people. Essentially what we're doing is we're breaking things on purpose because we want to make sure that we are going to survive. Because if you don't break it all the time, you don't know. Right? It's the same thing with backups, right? You can take all the backups you want, but if you don't practice restoring your backups once in a while, you have no idea if those backups are working. So 20 years ago, the best practice was to do a restore every month or whatever. For us, the best practice is to break things in production. We also have the Chaos Kong. The Chaos Kong doesn't actually kill the regions just yet. Right now, the Chaos Kong just takes all the traffic away from a region and moves it to the other region. But we would like to get to the point where we can destroy an entire region and bring it back up, see what happens. That's kind of our big goal for this year, is to try to get to that point where we can do that. Because as we expand around the world, it'll help us to be able to stand up new regions quickly. So we want to be able to do that, and for resiliency, right? If something goes horribly wrong in an entire AWS region, it's nice to be able to quickly stand up in a different region. Another really important monkey is the latency monkey. So like I mentioned before, we can inject failure because we have this shared library. And one of the big failures that we like to test is latency. Because detecting a complete failure is actually a lot easier than detecting a brownout situation, right? So when you have just slow or partial responses, that's actually a lot harder to detect. And so, we did the Chaos Monkey a few years ago. And when the Chaos Monkey first started running, it would actually find problems, right? We would destroy a machine, and that service would go down because it was not architected well to handle that type of failure. Now we're getting to that point with the Latency Monkey. Usually when we run the Latency Monkey, there's something breaks. And so we really are trying to get to the point where, with the Chaos Monkey, developers at this point know it's coming, and they just build around it from the start. They assume that their instances are constantly going to be destroyed, and so they just build for that assumption. We're trying to get in their mindset this idea of latency as well, getting them to just build with the assumption that you're going to have latent calls, and to make things work that way. And because the latency will happen all the time, especially in a cloud infrastructure where you have issues with noisy neighbors, and you don't control that networking infrastructure, and things just happen, things like that. We also have a couple of other monkeys. The conformity monkey, like I said, it looks for things that are outliers, basically. And then other various monkeys, janitor monkey, howler monkey, those things clean up and tell us about security issues, stuff like that. So now I want to tell you about some of our best practices. These are kind of some of the things that we've learned running a distributed architecture with the distributed development. So engineers are really good at reading a clock. When we ask them, please make sure that the time of day and week that you're going to do a deployment is a good time to do it. So we tell all of our engineers, our peak traffic is from about 3 p.m. Pacific to 11 p.m. Pacific in the Americas and roughly the same equivalent in Europe. And so we tell developers, if you have to pick a time to do a deployment, that's not a good one to do if you can avoid it. And they're really good at reading the clock and figuring that out. They're also pretty good at figuring out the risk of their change to their own service. Right? So in the service-oriented architecture, you want to know if your service is going to break with the change you're making. Sometimes you're going to make a higher risk change, and so you'll do that at a more opportune time, things like that. And so developers are pretty good about thinking about that one as well. But what we really try to get people to think about is the risk that they're causing to others. So in this service-oriented architecture, we all depend on everyone else's service, right? And so it's really important for you as a service owner to think about how the change that you're making is going to affect others. What you might look at as a very innocuous change might be doubling your traffic to one of your downstream systems, right? And you need to think about that. You need to think about how that's going to affect your downstream system. Maybe you go and reach out and talk to that person and say, hey, I'm about to double traffic. Is that going to be a problem for you? And sometimes they'll say yes, and sometimes they'll say no. But the important part is to think about that. And to think about who depends on you. If you make a change, let's say you're going to make a change that's going to increase your response time by 10%, which doesn't seem like that big a deal. But your caller might really care about that 10%. And so we're really trying to get this idea of, in this microservices, service-oriented architecture, you really want everybody to think about how their changes are going to affect everyone else. Another one of our best practices is not technical in any way. It's an incident review. I've worked at companies before where the purpose of an incident review was to determine whose bonus was going to be deducted for that outage. That's not a good purpose for an incident review because then no one wants to go and everyone just spends the entire time blaming everyone else. The purpose of our incident reviews is the opposite. We want to know what happened and figure out how we can make sure that that doesn't happen again, that that class of things doesn't happen again if possible. So really, it's a collaborative environment. People want to go to incident reviews. When we have an incident, they ask, when is the incident review? I have some great findings I want to share with everybody else. And so that's really our purpose of incident reviews. And our goal state is to produce a very concise write-up of what happened, why it happened, how we can avoid it in the future, and ideally come up with a set of action items that will prevent that type of problem in the future. Another one of our best practices is to not have typical policies. So our general state of affairs is to remove policies as we grow bigger. Most companies, they have very prescriptive and flexible policies, and as things break, they add more and more policy. But we like to, play it a little riskier, and so we actually like to make our policies a different way. We try to make them descriptive and flexible and evolve. So when we say policy, we really mean best practice. And the reason we do this is because we really want our our developers to be able to do what they think is the right thing to do. So we really don't have any strict policies. There's, when you make a change, it's advised that you put in a change request to document what you're going to do, but it's not required. And things like that. And we're trying to even eliminate the need for a change request. So some of our software, for example, we're developing to make it so that developers don't even need change requests because we have such good information around what's changing all the time that it won't matter. And that's kind of our goal, is to remove these barriers, these policies. Another one of these is this idea of circuit breakers or bulkheading, as some people call it. So when you're in this distributed architecture, one of the really key things here is detecting when things are broken that you're calling because you're depending on them. And so we have this thing, it's called Hystrix, also open source. Essentially what it does is each individual service keeps track of all of the people that it's talking to and whether they're returning good responses in a timely manner. And so each individual caller will monitor each of its individual dependencies, and if it gets really bad, it'll open the circuit. So if you remember your electrical engineering, an open circuit means that the electricity is not flowing, so the data doesn't flow. Essentially, it immediately returns a fallback response so that that other service can recover. One of the nice side effects of this is that it helps avoid thundering herd. So when the service returns, in a typical case, if you have a service that goes down, as soon as it returns, it often goes down again because it's suddenly getting hammered with a ton of requests all at once. What the circuit breakers does is it smooths that out because each individual instance is checking at a different interval and will come back and make that request again at a different interval. And so you'll slowly get this ramp up again of requests coming into that service to hopefully make it so that it doesn't just fall over again when it's getting all these requests. And so this is what makes people good citizens in the Netflix environment, right? We tell them you should use circuit breakers not only to protect your service from the people you're calling, but to help your fellow services where you are calling. So if they run into trouble, you are not making it worse. So this is another big best practice for us, is this idea of keeping track of your dependencies and helping them recover. We have a bunch of best practices for data. A lot of them I already talked about. Things like having multiple copies of all the data and keeping it in different zones, different regions, things like that. For those of you using Amazon, if you're using EBS, another good best practice is to take a snapshot of those frequently. Amazon doesn't make it super clear, but the reliability of the EBSs are only for data that's been snapshotted. They make no guarantees about data that's not snapshotted. We actually just avoid EBS altogether. And no secret keys on the instance. Luckily, Amazon made this a lot easier with their service to keep track of keys for you. So very briefly, I mentioned that we do multi-zone. And the benefits of those zones are they're loosely connected. We also went multi-region last year. And the nice thing about multi-region is that you can theoretically do 100% uptime. I like to say that because somebody inevitably tells me that I'm an idiot. But there are costs associated with that. But last year we did go active-active, which was, there was a lot of problems we had to solve about replication. How do you get the data across? How do you deal with a sudden influx of traffic to the new region? You're essentially doubling the load, right? When do you fail over? Things like that. We had to come up with cache replication strategies for, we created 3 strategies. So this goes back to our self-service idea. So this is all built into EV Cache, which I mentioned a couple of times, where you can choose which replication method you want to use for your cache data between regions. We created a sane default and validation only, but we give our developers the option of actually, and we encourage them to write their code so that they don't need cache replication, for example. But we did give them the option to even do a full copy of the cache if they really needed that. We had to deal with like traffic routing and failover. How do you scale up without getting overwhelmed? Do you fail over at the first sign of trouble? No, because you got to figure out that balance. But the nice thing is that our developers don't have to deal with any of this because this is all built into the platform. And that's the idea, is putting it all on the platform so really the developers don't have to think too hard about it. If they take the defaults, it'll probably just work. Now, some of the services do have to think about this if they're data-heavy services or things like that. But for the most part, we try to make it as little thought on the part of the developer as possible to worry about multi-region issues. Quick example, so this is the traffic graphs for when we did a failover test. And you'll notice that as the traffic was dropping in, or increasing in the west, it was correspondingly dropping in the east. And at the same time, Europe was unaffected. And that's really what we want, right? If we're shifting traffic around in the United States, we don't want our European customers to get affected by that. It turned out that as we were developing this, before we had ever actually tested it, we had a regional issue. And so we decided that our first test of our failover was going to be to do it live in production, because that was still better than having half of our customers out of, not being able to stream. And so we did. We just turned it on and to see if it would work. And luckily, it worked out pretty well. You can see the huge spike there where suddenly the traffic mostly came back, and it took a while to recover. And it was a great learning experience for us. We used, we had an incident review, and we learned from that experience, and we figured out some more tweaks that we could make to make that process better. But this is just a great example of our belief of testing in production. How does Cassandra fare through all of this? So the Cassandra team in their hubris created this image showing the Cassandra logo eating the monkeys. because they're unaffected so far by most of the tests. The Chaos Monkey, they can handle loss of a node no problem. You know, even in regional failure over, the system just keeps right on running, etc. So Cassandra has been very powerful in that idea of reliability. Just a quick reminder again, so a lot of the stuff I talked about today is open source. It's on our GitHub page. Please check it out. Also, if you liked what you heard, Netflix is hiring. And so I have like 4 seconds for questions. Yeah. Well, if you have any questions, this is how you can find me, or you can come up and I'll be here for a little while afterwards. So thank you very much.